Hello and welcome to the Data Engineering Podcast, the show about modern data management. Introducing RudderStack Profiles. RudderStack Profiles takes the SAS guesswork and SQL grunt work out of building complete customer profiles so you can quickly ship actionable, enriched data to every downstream team. You specify the customer traits, then Profiles runs the joins and computations for you to create complete customer profiles. Get all of the details and try the new product today at dataengineeringpodcast.com/RudderStack. You shouldn't have to throw away the database to build with fast-changing data. You should be able to keep the familiarity of SQL and the proven architecture of cloud warehouses, but swap the decades-old batch computation model for an efficient incremental engine to get complex queries that are always up to date. With Materialize, you can. It's the only true SQL streaming database built from the ground up to meet the needs of modern data products. Whether it's real-time dashboarding and analytics, personalization and segmentation, or automation and alerting, Materialize gives you the ability to work with fresh, correct, and scalable results, all on a familiar SQL interface. Go to dataengineeringpodcast.com/materialize today to get 2 weeks free. This episode is brought to you by Hex. If you're a data person, you probably have to jump between different tools to run queries, build visualizations, write Python, and send around a lot of spreadsheets and CSV files. Hex brings everything together. Its powerful notebook UI lets you analyze data in SQL, Python, or no-code in any combination and work together with live multiplayer and version control. And now, Hex's magical AI tools can generate queries and code, create visualizations, and even kickstart a whole analysis for you, all from natural language prompts. It's like having an analytics copilot built right into where you're already doing your work. Then, when you're ready to share, you can use Hex's drag-and-drop app builder to configure beautiful reports or dashboards that anyone can use. Join the hundreds of data teams like Notion, AllTrails, Loom, Mixpanel, and Algolia using Hex every day to make their work more impactful. Sign up today at dataengineeringpodcast.com/Hex to get a 30-day free trial of the Hex team plan. Your host is Tobias Macey, and today I'm interviewing Louis Brandy about building vector indexes in real time for analytics and AI applications. So, Louis, can you start by introducing yourself?
Hi. So first, thanks for having me. My name is Louis Brandy. I am the VP of Engineering at Rockset. I've been here for 2 years and change. Prior to that, I was at Facebook for 10, 11 years doing infrastructure stuff and spam fighting for many of those years, specifically infra for spam fighting. This turned out to be surprisingly useful in my current role because we've wandered into this real-time space. AI and vectors are emerging. So that's part of what we're going to talk about today. And this is what Rockset is well designed to do. And so I have some of my old things coming back with my new things. And I think that's what we're here to talk about. So yeah, that's the very short version. I'm happy to give you a longer version if you'd like, but I think that's enough for now.
And do you remember how you first got started working in data?
So I came into data backwards. Like this wasn't a thing I decided to do entirely. It actually started with the spam fighting stuff many years ago. When you're doing spam fighting, a lot of data problems are very real. It's super important that you have data, but the requirements are very different. So for example, in spam fighting, I would much rather have like 1 second old data instead of 10 second or a minute old. But I can lose some. It's okay to lose a little bit because I'm just fighting spam. If I kill 99% of it, that's good enough. Most data systems, this is not, most data systems will not make this trade-off, like lose a little bit of data, but be a lot faster. That is not a thing that most data systems can tolerate. So we were building a lot of custom data infrastructure to meet the needs. And that got us into it. Then we're all of a sudden learning about how people do this, what kinds of systems do you build and have been built. And I was mostly an infrastructure person at the time. So data infra obviously are very tightly related, but not entirely. So I spent a lot of time doing distributed system stuff and even C++ stuff. I did a lot of core libraries type work, RPC type things, even build system and things like that at times. But data was very important because in a lot of these, obviously, infrastructure and the data infrastructure is the most important distributed systems at these large places are data systems, and so they are inextricably linked. So that's how it got started. And then obviously when I came to Rockset, I was much more of I still am. I consider myself more of a distributed systems person than a data person from my background. We have proper database experts here. I'm allowed to say that because they sit over here and they really know their stuff. I do my best to hang with the proper database experts, but even still, sometimes I'm still catching up to some degree in that world.
Yeah, well, most of data engineering these days is just stitching together different distributed systems and hoping you know enough about how they work to actually make some sort of useful pipeline out of it.
Exactly. We're all in the same boat together to some degree.
And so, in that context, I'm wondering if you can just start by giving an overview about what vector search is and some of the ways that it differs from other aspects of search that people are likely familiar with.
So we could give a really long answer to this question. I will try to give a short answer. Maybe it's worth diving into some of the details. At a very high level, vector search is about it fundamentally is in two stages. One is like turning a very unstructured search problem. Hey, find me things that I'm interested in into a structured search. And the structure here is specifically you project whatever unstructured question you're asking into a vector space. And then the structured question you're now asking is, given this input vector, what's the closest vectors to that vector? That is the search. That is what I've defined the search to be. What are the nearest neighbors to this vector in this vector space? And how you generate this vector space, like how do I go from something like all the restaurants in the world and some data about me to you answering the question of project me into the vector space of restaurants and find the nearest restaurants to me in that space, not physically to me, although physical distance would matter, that's like a gigantic problem. I mean, that's literally what, to a non-trivial degree, what is being revolutionized at the moment is this precise problem. Like the OpenAIs of the world are revolutionizing the quality with which we can embed a particular unstructured piece of data in a vector space. So, 15 years ago, that's overstating it. Let's say 12 years ago, I was doing this kind of stuff at Facebook. We were doing like text-based vector embeddings to do, for example, like spam detection. Like show me stuff that looks sketchy based on a previous definition of sketchy. We were doing vector similarity, but our vectors weren't very good. They were good. It was actually quite surprising how effective they were, but the vectors of today, I suspect, are much better. Much, much, much better. That vector space, so to speak, is a far better, the distance metric in that space is semantically valuable in a way ours weren't. And again, there's a lot of research behind this idea of semantic value. Like, what does it mean for something to even be close in some space? And so this is the core idea of vector search. It is, in some sense, the vector, it becomes the lingua franca of these two sides. So getting from your very hard unstructured problem into vectors is like a kind of an ML AI type of problem. It doesn't have to be, but typically is where we thought of this. Once you have vectors, well, now it's like algorithm. We're in algorithms class now. Now it's like, all right, I have a billion vectors. The distance metric in this space is, let's say, Euclidean. It doesn't have to be, but let's say it's Euclidean. This is like a bad interview question at this point. Like, how are you going to find the closest one to the input vector? It's a super well-studied problem. And within that problem, there's a bunch of other known hard technical problems, which we could talk about. We actually think we should talk about. And so a vector database's job is to do this for you efficiently, performantly, cost-effectively, accurately. And because of the increasing value on the left-hand side of this equation, meaning the generation of vectors is become extremely good, meaning it's preserving a lot of semantic value in these vectors, the corresponding problem of vector search is that's what extracts value from the left-hand side. So that's becoming an extremely hot area for people. So there's another intersection here, which is that Rockset is a real-time data platform. That's its roots are in real-time data analytics. There are different systems that exist in the world like Rockset, but the architecture of those systems is very similar to what you want for something like a vector database. So it turns out these two somewhat disparate areas are actually architecturally quite similar under the hood. And so this is why certain kinds of databases can quite naturally add vector search as an extension to what they're already doing, because they're already kind of built to do this well. And again, this is another topic worth we could fill hours on this if we wanted to go into the details. But this is why Rockset is sort of getting into this space, is because it's actually a natural extension of what we're already doing. So so that is an overview of the vector area. I don't know if that totally answered your question. I don't know if there's how much we want to double click on anything I said.
No, that's definitely a good framing for the conversation. And I've had conversations in other episodes about vector databases and some of these challenges about kind of generating those vector embeddings. But yeah, to your point, it's largely the data engineering question of how do you get this source data into this other representation, which a lot of times does require some sort of ML algorithm to build those vector representations. And then it's, as you said, linear algebra is just a matter of how you want to represent that distance metric. Digging more into the technical aspect of building a vector search capacity for a particular problem space. I'm wondering if you can talk to some of the technical challenges that are associated with the end-to-end workflow. So what we talked about a little bit already of generating those vector embeddings, having that vector database, having clients that are able to understand those vector representations for being able to apply those search interfaces, and just kind of what that means to have vector search as a capability within an overall either data pipeline or data platform or data application, particularly in terms of how that would juxtapose with maybe a full text search that people might already be familiar with.
It's useful to ground this in an example. So text search is a good one that you can use. So typically people are probably familiar with like full text search or keyword search or these kinds of like, find me all the documents that contain the following string kind of queries on a text corpus. The idea where vector search becomes valuable is you would, in theory, you would have a very smart ML model that you've trained, which is beyond our conversation, right? And its job is to turn your text documents into this, embed them in this vector space. And then typically when I ask a query, I can then go search documents that are like it. And again, like it is this typically framed as like a semantic search. Hey, show me all the documents about, launching, satellites. And it's like, well, it has some notion of what that means, and it's able to find documents like that. It's this idea of semantic search. It's interesting because you mentioned technical problems. And I think if you're really early in this, you can imagine thinking this and being like, oh, I can see how that could be useful to have this kind of like fuzzy semantical type search instead of this very exact sort of substring based search. Anyone who's actually tried to do this in real life, I think very quickly realizes you run into some very specific problems very quickly, like super fast. It'll happen as you try to turn something like this on. The first and most important one is these are independently useful. And you actually almost always want both. You almost always want like, hey, show me documents involving satellites that contain the specific keyword, whatever. I don't know anything about satellites, I don't know, Sputnik, I don't know, right? You want these like hard guardrails, like in the restaurant case, like, hey, give me restaurants within 100 miles of me that are not expensive, that I might like. The I might like part is this vector-y kind of semantic, in this case, search. But all these other things are like very concrete metadata that I really, from the product experience perspective, are sort of non-negotiable. Like if I ask you to give me restaurants within 100 miles, I don't want something 200 miles away. Like that's weird. Even if the vector says I would love that restaurant, it's a weird product experience. And so joining these two together, these two kinds of searches together, is actually a very hard problem. And so a lot of people will get hung up on vector search as this like, okay, cool, I have this cool semantic search capability, but sort of naked vector search is almost never great on its own. Sometimes it is very good, but most use cases need to combine these kinds of searches together. And this is a really hard problem in a vector database setting, or I should say database settings in general. But this metadata filtering problem is really important, and it's a very difficult one to solve. And I actually think it's underestimated how important this will almost always be in a vector search use case. So that's my one big problem that you'll run into. The second really hard technical challenge when you're doing vector search is incremental indexing of vectors. So the other thing that people really have to understand about vector indexes is they're very monolithic creatures by nature, at least as of today, meaning I give you 1 million vectors. You work really, 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 really hard to make them searchable. And if you give me one more, there's no good way for me to add it to the index in a way that preserves the index's fast lookup capabilities. Obviously, I can add one. It won't deteriorate too quickly. But if I'm constantly streaming new vectors into this thing, it deteriorates fairly rapidly and loses its fast lookup properties. And so if you're in a world where I can train this thing every night, and yes, I can train you on, I can give you vectors from yesterday because I trained it overnight. We're great. Things are good. So I always use the example of Spotify. Like music doesn't come out that quickly. So if I train a massive vector thing overnight for new music, then that's going to work pretty well. But if it's something much more rapid that's happening, it's a very, very difficult problem to keep your vector index both fast and up to date at the same time. So these are my two very hard problems that I think vector solutions. Frankly, there's more hard problems because you actually mentioned something very important, life cycle. There's actually a third hard problem here. We're too zoomed in. If you zoom out, there's a life cycle problem of like, okay, great, I have 1 billion vectors. I got a new model now. How do I update this gigantic thing without overloading my database or whatever? Like, so the lifecycle management of your vectors, I actually think is another very hard kind of data management problem. These are kind of, I think, the big three maybe of like hard problems that we as data people need to take much more seriously and do a much better job for our collective users. The data infra people as opposed to the data users. All three of these are very hard problems. So these are problems we are taking super seriously. I mean, other people are also trying to make progress on them, but I would encourage anyone that is like interested in like building in a vector search capability to ask these questions of whatever solution you're thinking. Like, what are my needs for incremental indexing? What are my needs for metadata filtering and lifecycle, like vector lifecycle? Ask those questions at the front. Obviously, you may not get good answers, but that's okay. You want those answers now rather than to not ask those questions.
And there are a number of more detailed aspects of this that I really want to dig into, but I'm going to delay them for a little bit in favor of the question about what are the cases where vector search is such a high value add that it is worth all of the added complexity that we were just discussing.
So yeah, there's a good question. I think the historical number one dead center use case for vectors has been recommendation type system. So semantic search, the text search we just said, is a kind of recommendation engine. It's like, I give you this query, recommend things like this. If you squint at it, it's a recommendation problem. But even more classically, things like, people you may know on Facebook, or hey, you should check out the right pane on YouTube. Like, hey, these are videos you might want to click on. Like that, those kinds of features historically have been very amenable to machine learning techniques in general, but vectors in particular. So, every user is a vector in theory. Every streamer or YouTube video is a vector in some sense. And so these recommendation engines being powered by vectors is a very classic use case. Amazon, another very good use case. Hey, people that bought this also buy this other thing. This is a dead center vector type use case that, to be clear, hasn't always been done with vectors. This is another rabbit hole. You can build a bespoke classifier for all of these systems, and people often do and have. So there are different ways of approaching that, but that kind of thing is very much the kind of thing that vectors have historically been very good for. We should point out, just for completeness, low dimensional vectors have been also very useful for a really long time. It's typically not what we're talking about when we talk about vector search. So even very low dimensional vector, like geodata. So find restaurants near me is a vector search problem, but it's in low dimension, 2-dimensional vector search. So there's also a huge universe of stuff to talk about in that particular vein. But I think those are the two classic cases. Obviously, there's a new one that just occurred in the last year, which is this kind of LLM model. So a lot of these large, like chatbots have, if you've ever, I don't know how many people have cracked them open and see how they actually work. There's a very large vector component to how chatbots work. So as a very simple example, you could imagine training a ChatGPT-like thing on your internal documents so that it can answer questions about your own internal business. You could say like, hey, when I use this library, what happens? And your little internal ChatGPT could tell you about it. But inside, under the hood, that same question gets turned into a vector and could return, like as a semantic search, the results. Like, here are the internal documents that would answer your question were you to read them. And that's kind of how the ChatGPT kind of thing would work. It sort of says like, hey, do this vector search, find these documents, and then summarize this for the user who asked this question. That's kind of what the robot is doing under the hood. And so that's much more expensive than just returning the documents to the user. It's computationally more expensive. But this is like an emerging place where vector search is actually either a partial solution to the thing you wanted to build or part of the implementation of the thing you wanted to build. So people that are building chatbots are all kind of looking at vector search and vector database technologies to help power those things. So I think those are the main, I shouldn't say the main, but at least the most common use cases we're seeing.
Yeah, with the increasing attention in large language models and applications built on top of them, I've been hearing vector search and vector databases come up more frequently than over the past couple of years, which is around when I first started hearing about vector databases to begin with. And to that point, a requirement for being able to apply these vector search or vector index capabilities to have a dedicated piece of database software that is focused on these vector indexes? Or is it something where you are able to take advantage of these nearest neighbor searches for vectors without necessarily having to add a dedicated piece of infrastructure for this specific problem, where it's something that can be encompassed with other technologies that might already be part of your stack?
So I think you've asked the most important question of all, because I have very strong opinions here. And I have many hats that I can approach this question from. So obviously I'm the VP of engineering at a database company, so I'm gonna have opinions about this. But even in a former life, like at Facebook, nobody wants to run another thing. The cost of running another thing is always super high. You better have a really good reason to run a new thing, whatever the thing is. I think there's an even more pernicious problem here that is actually maybe the thing I think the most, which is a vector database is much more database than vector. Like in real life, if you're going to run a real vector database that's going to solve a real production issue, most of the things you need from it and the problems you're going to have with it won't have anything to do with the vectors. How is this thing, managing its memory? How is this thing, what is its durability? How do backups work? How does access control work? How does atomicity work? And what is the consistency model of this thing? These are all database problems. This is here, take this database textbook, get to work. At the very, very end, we'll implement some cool vector search algorithms, but we have a mountain of database problems to solve. There's no denying it. And so to me, I don't actually think here, I'll make a very controversial claim for you. I don't think vector databases are a thing in the sense that they're databases. It's a database. It's in the end, all vector databases will be databases because it's just another index in a database. And all the database problems there's still a mountain of them. And so whether or not it's better to add vectors to an existing database or whether you should add a database to some vector search algorithms, I think it's much easier on average to add a vector index to an existing database than it is to build a database around a vector search algorithm. Obviously, that's going to depend on a particular problem and what your actual requirements are. I think most vector search use cases can get away with just having a vector index in an existing database, not building a new thing, not adding a new thing. This gets us into a slightly more treacherous waters, which is real-time analytic databases are much better for vector search than, for example, an old school, I shouldn't say old school, that's actually a terrible word. A transactional database, you still need one of those. It's not old school. You should have one of those. You need transactions almost certainly in what you're building. Those databases, though, are architecturally not quite as good for doing high performance and efficient vector search. And it's the same reason analytic databases like OLAP style databases are different from OLTP style databases. It's exactly the same architectural difference is what makes those analytic databases good for vector search, and transactional databases not quite as good. But obviously you can still do it. It's just as a general rule, I don't think you want your vector search going to the same database processing your transactions, because for many reasons, but the first and obvious one is you're going to DOS yourself. The transactions are kind of actually more important than everything else. It's more important that Amazon bills you properly than it recommends smart purchases, right, for you. And so there is this separation, right? OLTP and OLAP databases. They were driven in those two architectural directions for a reason, and it's actually the same reason to a large degree why vector search ends up being really good in this kind of analytic type database environment. So my opinion is OLAP style databases adding vector indexes is an extremely good way forward, and I think in the end it converges there. Vector databases will look a lot like OLAP databases, and OLAP databases will add vector search capabilities, and these will almost always be paired with an OLTP database. So I'll have Postgres over here and maybe Rockset over here. And that's actually the data stack for, again, an abstract problem we haven't defined. But I think that's actually kind of the path forward. And my suspicion is there won't be a third category called vector database. They will just be vector heavy OLAP databases is kind of how this will look over time.
You shouldn't have to throw away the database to build with fast-changing data. You should be able to keep the familiarity of SQL and the proven architecture of cloud warehouses, but swap the decades-old batch computation model for an efficient incremental engine to get complex queries that are always up to date. With Materialize, you can. It's the only true SQL streaming database built from the ground up to meet the needs of modern data products. Whether it's real-time dashboarding and analytics, personalization and segmentation, or automation and alerting, Materialize gives you the ability to work with fresh, correct, and scalable results, all in a familiar SQL interface. Go to dataengineeringpodcast.com/materialize today to get 2 weeks free. For teams that have decided that it is worth their time and effort to incorporate these vector search capabilities into whatever problem that they're solving, who do you see as the typical owners of the data flows, the data modeling, the system architecture around these vector capabilities? Is it usually the data engineer, the data scientist, the ML engineer, data architect? I'm just wondering, what are the ways that incorporation of these vector embeddings, vector search, influence the team topologies and how they approach that problem?
Okay, what a great question. Yeah, I don't know, but not in the simple sense of the phrase. I think the way this ends up looking is very similar to how some of this stuff looks today, with how you might imagine an OLAP database or an Elasticsearch cluster being run in a large enterprise. So it's typically like a data infra type team or data engineering team that is like owning this thing. And there's a bunch of other teams, data science and things like that, using it, sometimes abusing it. Everyone knows that those systems get abused. And basically, you talk to any team that owns one of these systems, they'll tell you all the ways that other teams are being clever and abusing it. And I think vector search fits very squarely into that space in your brain, for all the same reasons that you might put something like an OLAP database into your stack. I think vector search ends up fitting in a very similar. I think that there's a good analogy, like when you think about team topologies, to think of it just like that. The same reasons you might add an OLAP database or something like Elasticsearch. I think that that's roughly where a vector search will fit in. So typically it's going to get run by a core engineering team that owns it, and many other teams will use it if it's widespread. Obviously, the other way that it happens will be the team that wants to build the feature will set up their own infra, and maybe it's bespoke to that one team, and that kind of setup happens every time. But that ends up being gnarly over time. Like, it's always dangerous when a team builds a piece of infra for the feature that they want. So I don't know if that answers your question. I think this is to some degree still emerging rapidly, but my view on this is that it's like data infra type of an organization will own this feature. It will be part of the core data stack. It will be a primary feature of one of your core pieces of infra over time, and then everyone else will use it and possibly abuse it.
The other interesting aspect of this is the data modeling question, where you have in transactional databases and tabular resources, you have a very familiar syntax of columns and rows. You know what they're supposed to mean. When you start to deal with vectors, they're a very abstract concept. It's just a mathematical structure with different values within a matrix. And unless you are very deeply invested in the problem domain and what it is that's being represented, if you look at it, it's just a bunch of gobbledygook. You have no idea what it's actually supposed to try and tell you. And I'm curious, what are some of the ways that you've seen teams try to apply meaning and context to these vector records so that somebody who's looking at the ways that they're generated or trying to understand kind of what the meaning is supposed to be semantically for this particular search problem that they're trying to solve for, how they can start to think about either adding appropriate metadata, but also in particular, as the vector representation evolves, how you think about that migration process?
So the way I think about vectors is as a pile of gobbledygook. I actually think that's the most healthy way to think about them. So in a tabular form, there is a column called my vector embedding, and it is a bunch of numbers that is basically meaningless, except for the operations you can perform on it. And so I actually think thinking of it as a tabular form is the most healthy way to do it. So I have an image table, and here's the source image, here's the uploader, here's the time. My classic. You can invent your database schema for this, but over on there in the end, like one of the last columns will be the vector embedding, for whatever kind of model generated this, right? And so you may have more than one, because you may have more than one model that is embedding it for different definitions of semantic relevance, right? So a very simple example is like the kind of model I would use in spam fighting is very different than the one I would use, for example, in image search. Like, show me images of elephants. I want a very, very specific kind of model that understands elephants. But in spam fighting, I actually care more often about near duplication. I don't actually care about images of elements. I want things that are fairly similar, like almost near identical. I'm looking for things like, I want it to be like resistant to rotation or cropping or light balance changes, things like that. That's a very different notion of closeness when we're talking about semantics. So you may have more than one column that is a vector, but to me, so to be concrete, like you and I know a vector is a bunch of numbers. So maybe you might think I should have a bunch of columns that represent a vector, but I would say no, because there's no relational value. I mean, I shouldn't say that. I think it's very healthy to not assume there's any relational value within a vector. Like you never want to write a query that's like, show me all the vectors where the 15th dimension is above 42, or the 23rd number is less than the 47th number. Like that's not a thing that I know of that is going to ever be valuable. So as a general rule, I think of a vector as just a new column in your database that you have built an index on, just like you would any other column, except this is a very specific kind of index that has some of these peculiar properties. For example, it's very hard to incrementally update. And this model also highlights this whole metadata filtering problem. Like it gets you back to this very hard problem that we talked about. It makes it very natural to want to talk in these terms, right? Like when I say, show me all the restaurants like this, what I'm saying is, show me all the restaurants, like order by this vector column, distance in this vector column is my SQL. I'd order by that, limit 10, where, my where clause, where it's Italian. So I think that's the right way to model this. And it fits naturally into a SQL type mindset. And it also, it reduces to language we understand, right? You have this where clause that is your metadata filter. You're order buying typically distance, and that's your vector search problem essentially. And that tends to be how I think about it. Now there is a much harder problem of like understanding these vectors. That's like an open research problem of like, what does this even mean? Like what is the semantic meaning of the 15th dimension number? The fact that you're a 45 and I'm a 13 in dimension 15, is there any meaning to that? As far as I know, this is like an extremely unsolved problem. It may be unsolvable. And so I think from a vector database and data, the data user's perspective, I would think of it as gobbledygook. I think that's actually the right way to think about it. It is a bunch of numbers that you can perform functions on that give you semantic meaning.
In terms of the consumption side of things for relational databases, tabular references, there's a large array of software and libraries and technologies that understand how to work with that data. I'm wondering what you are seeing as the current state of the ecosystem for clients that are dealing with these vector representations, for being able to understand how to structure the queries, how to interpret the results that are given back, some of the ways that factors into the overall system design of the data applications that are interfacing with these vector search capabilities.
Okay, you've asked a good question. You made me think a little bit here. The traditional databases have this advantage that we talk to them in a relatively universal way, and they give us an answer in a relatively universal way. So you could build tools that, you could build, like there are a lot of libraries, like great visualization libraries. Let me explore my SQL database relatively straightforward way. What is the equivalent for that in the vector world? I mean, the answer I think is clearly there is none at the moment. And it's in part because like a lot of our first principles aren't even the same. Like you don't talk to vector search in a universal way at all today. We're building it like SQL. So for us, it's trying to fit into this existing model where if you have a SQL, if you have a tool that knows how to interrogate via SQL and visualize something in an interesting way, I want to make that work for us in sort of that paradigm. But there are other, like some of these tools don't even use SQL. Like it's an API call, and in a generic sense, there is no generic sense in which you can interrogate one of these things to get answers. And then certainly it will return you answers in a very different way. Obviously, in a simple sense, it's going to return you vectors, but typically there's metadata associated with those vectors. So there's like either you have data there, or you might want to do something like a join, the moral equivalent of a join on the answers that come back. And so now everything becomes very bespoke. So we are trying really hard to make this a conventional player in the ecosystem. Like if you think of vectors as simply data that's in your database that you could join with other tables and that you can perform searches on and that you have indexes on, it will play nicely with everything else that has been built above and around it. But that is not by no means the emerging standard at the moment. I don't think this is standard at the moment. So I think the correct answer to how are you going to do this kind of stuff is going to depend exactly and precisely on the tool you happen to choose today. And it will be easier or hard depending on the specifics, because I don't think we've standardized this at all. So I think some of our like first principles, like our we don't have lingua franca entirely established here. And so I think things are messy at the moment.
And in your work of building a database technology that is aimed at supporting this vector search capability, what are some of the aspects of customer education, logistical challenges, logical challenges that you're seeing teams try to tackle in the process of adopting these capabilities, integrating them into their data stack, adding them as a feature to their existing suite of data platforms and data technologies?
Yeah. So logistical challenges. So there's a couple ways I've interpreted the question. So the first thing that comes to mind is one of the things we're seeing a lot of is a bunch of businesses and teams that like know something is happening but don't understand, does this apply to us? Does this matter? Am I like are my competitors about to do something that I don't even know what's happening and destroy everything? Like they're like trying to figure out, does this apply? Is this just something those crazy people over there are doing? Or does this apply to what we're trying to do? So like finding a path to like, in our particular business, the problems we actually face, is there a place here for this like rapidly emerging technology? So that's one area of customer education that I think is, it's hard. I mean, we're talking to lots of customers and there's a lot of brainstorming happening here about how you might use some of this stuff in a particular business venue. It's not always clear to me that there is a good use case, and that's okay too, obviously. So that's one area that's very hard for customer education. The other part that's interesting is we're pretending like it's two people talking, but when two organizations talk, it's actually a lot of different people talking. And so you might have like like the team that's owning and operating the infrastructure versus the team that wants to use it. They have different needs and wants and hopes and dreams. We actually covered some of this earlier, right? Where it's like the product teams might think this is useful, but the infra teams are like, okay, but I don't want to run another thing unless you tell me this is really going to be useful. So this part is also quite hard. Typically, the team that is sort of wanting to build and the team that has to own this thing and run it and pay for it, so to speak, isn't the one who necessarily wants it. That's not a thing that's going to power something important to them. So understanding like what the real business value is here and getting a business to understand that value, I think, is also very important in this kind of, because it's complex, it's emerging, it's not obvious how this fits in to an organization. And then again, there's another meaning of the word logistical, which I kind of latched onto, which is like the sheer problem of managing this is large. Meaning, if I have 1 million vectors, that's probably not too bad. If I have 10 million or 1 billion, it's a lot of data. And then I need to update it. I need to keep track of it. I need to imagine I have to run this really expensive model, a new version of it on 1 billion vectors. That's like a huge compute job that needs to get orchestrated. That's a massive piece of infrastructure that has to, and typically your vector database doesn't solve this for you, meaning you don't want to run a massive retraining job on your database, because that's gonna DOS whatever it's running in real life. So you have to come up with there's a massive logistical problem here of just like, how do I retrain this thing? How do I update this thing? How do I deal with rerunning my model on 1 billion vectors and storing that and keeping my site up while I do that?
And in your experience of working in this space, talking to customers, applying these technological capabilities to the problem spaces where they make sense, what are the most interesting or innovative or unexpected ways that you've seen these vector search capabilities applied?
So my favorite use case it's a traditional use case, but it incorporates a lot of things that are subtly hard. And it's one of those good examples of small details matter a lot. They make the problem go from easy, and I'm using scare quotes on easy, because the problem's not, even the easy form of the problem's not that easy, to very, very, very hard very quickly when you use certain words. So we have a particular customer called Whatnot. Whatnot does live buying and selling. So I mean, it is essentially a union of like eBay and Twitch. The idea being, at any given moment, you can go to Whatnot, and if you're interested in buying Pokemon cards, there's someone live trying to sell Pokemon cards, showing them to you. You can interact with them, you can ask questions, you can buy stuff from them. So it's sort of a live marketplace. They have a classic vector search problem. Like, hey, I historically am into A, B, and C. Can you show me people that are that are selling A, Bs, and Cs, right? That is a dead center vector search problem. But it has this very, very difficult real-time online component, meaning, well, the user just decided today they logged in, they're going to sell Pokemon cards. Yesterday they were selling baseball cards or whatever. And so their vector is changed. It's suddenly a new vector, right? Because it used to be baseball, now it's Pokemon. And similarly, they're online right now. That is a piece of metadata that is associated with like right this second, as opposed to like they weren't online 5 minutes ago or an hour ago. And so they have a very real-time component to their vector search. Remember, we start all the way at the beginning. I was like, incrementally indexing is hard. Like, it's not a thing you want to do. Well, congratulations. Because they have this live component, it's incredibly important that their vector index is up to the minute or sooner, ideally, fresh, and that their metadata is fresh, right? So this like doesn't do me a lot of good to say like, hey, here's a streamer you would really love to watch, but they just went offline 2 minutes ago, right? So I have to have real-time metadata filtering, and I have to have real-time indexing, effectively real-time indexing. And so those two requirements radically alter the question of vector search. It's a much more technically treacherous territory now, because it doesn't really do them any good to train some giant model overnight, because everything could be different tomorrow. I could log in at any moment and I could sell whatever I want. So I really need this thing to be nimble. And vector search indexes are not, if there are many things, but nimbleness is not something that they have that comes naturally to them. So first of all, these kind of real-time systems like Rockset. So I mean, Rockset comes from a real-time analytics world. So this is what we care about already. It doesn't matter if you have vectors or not. Like the idea of like, I need your data to be up to date when you search it, like as fast as possible, is like a core sort of part of our infrastructure. But that's where you start to get into like the really hard problems of vector search become very valuable from a product perspective, the product experience perspective. And so that's one of my favorite go-to examples of where you really are pushing the technology. For example, you could not just download a random vector search algorithm from the internet. You could find really good ones on GitHub, like right now, but they are not going to be good for incremental indexing, especially continuous incremental indexing. That's going to break stuff. So we're into like proper science territory now, where like, you know, people will write papers and PhDs will be given for people who make this particular part of vector search better.
This episode is brought to you by Datafold, a testing automation platform for data engineers that finds data quality issues before the code and data are deployed to production. Datafold leverages data diffing to compare production and development environments and column-level lineage to show you the exact impact of every code change on data, metrics, and BI tools, keeping your team productive and stakeholders happy. Datafold integrates with dbt, the modern data stack, and seamlessly plugs in your data CI for team-wide and automated testing. If you are migrating to a modern data stack, Datafold can also help you automate data and code validation to speed up the migration. Learn more about Datafold by visiting dataengineeringpodcast.com/Datafold today. And in your own experience of working in this space and keeping abreast of the changing technologies and the changing ways that it's used, what are some of the most interesting or unexpected or challenging lessons that you've learned in the process?
Yeah, I mean, at the risk of repeating myself, this incremental indexing problem is A+ hard. The metadata filtering problem is A+ hard. One of the other challenges, I said a version of this earlier, but I will repeat it here. There is a grave mistake that anyone out there could make. I encourage you not to make this mistake, which is to not understand the difference between vector search and a vector database. It's not that hard to download a vector search library from the internet and start playing around. And you could build a really compelling prototype probably super fast. But you should take the next step very carefully. And the next step being, oh, we should launch this, because what you're going to do by accident is like sign yourself up for building your own database, like slowly and surely. Like very quickly, there'll be questions about, okay, what's the consistency of this thing? And what's the durability of writes to this thing? And what's the data latency to this thing? Et cetera, et cetera. Access control, right? I'm not telling you not to build your own database. I mean, I am telling you don't build your own database. But if you decide to build your own database, at a minimum, you should do that consciously. You should say, we are going to build our own database. Get in a room and be like, all right, we're going to build our own database. Like, don't just accidentally wake up one day and go, uh-oh, we're building our own database. Like, I have a whole team of people worried about transactional consistency. that seems like we've gone wrong somewhere along the way. So I think that's kind of my like main takeaway here. I think for teams, like this is more of my warning to the people that are starting to go down this road is there's a few early forks in the road that I want you to understand. You can take the different paths, just take them eyes wide open instead of the other way around.
And for people who are exploring these capabilities, trying to get a grasp on vector search, how it works, how to apply it to their problem, what are the cases where it's just absolutely the wrong choice?
Yeah. When is vector search the wrong choice? It's if you can't, it is all fundamentally built on the idea that there exists a vector space on which a metric preserves some semantic value, and you have a way of embedding your things in that. There are absolutely cases where it's not so clear that a vector space with a distance metric can model the question you've asked. And therefore, this is a terrible setup. A lot of these are trivial in some sense. So for example, keyword search is not a thing you should do with vectors because it does not map to a vector space particularly well. And in fact, there's actually a good example of this that's come up recently, which is like fuzzy string matching, right? So for example, like it's very like imagine you want to do keyword matching, but with typos. Like it's because humans typo. So like a type ahead. A type ahead is a very common thing that people want to do, right? Like I start to type in my thing and I want to give you some autocomplete or some suggestions. And I want it to be like typo aware. So if like the user makes one or two typos, it should still suggest stuff that's valuable, that might be completions for this. This problem, as far as I know, is not amenable to vectors at all. There's no vector space where distance is like edit distance, for example. And so this doesn't work in vectors, as far as I know. There are a lot of spaces like this where the modeling you want to do doesn't work in a vector space with a distance metric. And so I think for all of those use cases, you should avoid vectors. The other thing I would say is that are relatively expensive compared with traditional means. Meaning my database record has maybe like a 200, 300, 400 bytes in it historically, depending, for whatever I'm putting in there. But like an OpenAI text embedding is like 1,500 dimensions. So it's, several thousand bytes if it's 4 bytes per dimension. So just any normal query you would run is much more expensive when it's doing a bunch of vector stuff than it would be otherwise. And so there are probably use cases where, this might even be better with vectors, but it's 5 times more expensive or more, 10 times than like a trivial kind of SQL type query. And so maybe in that case as well, like is the ROI worth it? And there are probably many cases where it wouldn't be worth it at all. Like it's computationally a bad ROI. So I think that's another thing to consider when you're thinking about vectors.
As the overall adoption for vector search, vector indexing continues to increase, particularly with the increased application of large language models, what are some of the future potential applications that you see for these vector indexing, vector search capabilities that are yet to be realized?
I think that the correct answer to this is it's very hard to predict. And the reason I say that is because vector search is exactly as valuable to my business as the value of the embeddings that we are searching. So like the fact that we suddenly have a bunch of really high quality text embeddings suddenly makes something like a vector search for, say, chatbots or a natural language prompt as a search query. Suddenly that's really attractive use case because the embeddings are so good. So, if an equivalent embedding technology comes out for some other media, suddenly that's going to be super valuable use case tomorrow. And it will be almost a function of that. So in some ways, the limiting reagent in the future use cases is the value of the upstream embedding and how well it preserves semantic meaning, not the vector search piece. I will say, though, that in kind of the AI language, they talk about like multimodal. And I kind of want to talk about like non-modal, meaning like it's one thing to look at like an image and come up with an embedding, and then look at some text, come up with an embedding, look at a video, come up with some embedding. But like a lot of the problems that we are seeing it's virtually all the data of the universe is the input to this thing. So I'll get a trivial example here is like, I want to do fraud detection for payment processor. What is the data that I might pass in to say, is this transaction fraud? Well, it could be it's all the point in time metadata associated with that transaction. They want to charge this much money. This is the vendor, blah, 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 blah. But there's also like everything that's ever happened. What is the entire history of this vendor? What is the entire history of this region? What is the entire history of this of this payee? What is the entire history of like all of that? Turn all of that into a vector, put that into a vector space, and tell me if this transaction looks shady or not, is near previously known shady vectors, for example. That's the kind of thing where, again, the vector search problem is very straightforward. I don't know how to do that first part, like how to take that particular transaction and everything that's ever happened, the entire history of, I guess, everything before that transaction, and turn that into a vector I mean, I can turn it into a vector, but is it any good? And how do I make that vector better, that vector space better? That's a place where I would like us to make more progress. I would love to be able to help users who have problems like that vectorize them. I don't know how to do that with them today. And this is the kind of questions we're getting asked that I don't necessarily have great answers for today.
And that actually brings up another question that we didn't touch on yet, is the question of data quality in the context of vectors, where if you have tabular data, if there are numeric values in there, or if there are textual values, then you can say, this is the expected range of distribution that I should have for this column, or these values are outside of the usual type, so I can do some sort of anomaly detection on these static or scalar values within this tabular construct. Or even if you're dealing with unstructured data, if you have a JSON object, you can do some sort of anomaly detection there. I'm curious how that concept of data quality management applies to vectors, and if that is something that is still yet to be determined.
So when you say data quality, typically what I think about is like rogue data, like truly, like the data is nonsensical. It's not that it's anomalous. It's nonsensical, meaning somebody typoed something, or some bug has occurred. And it's interesting because in a vector space is like a dense thing. Like by definition, all values are valid. Like, so in a sense, it's very hard to tell that something is truly wrong in the data. On the flip side, it's easy to tell that something's anomalous. Like you literally have built a space that is intending to cluster things. So if something is anomalous by definition, if it's not close to anything else in this space. And so that might be because it's truly unique. Like the original thing is fundamentally unique in an interesting way. It might mean something terrible has gone wrong along the way, meaning there's a bug or some other quality issue has occurred. I don't know of any interesting work in this particular dimension at the moment. It's actually an interesting thing to think about. I am very interested in the problem of anomalous vectors, meaning imagine you're ingesting vectors all the time, and I want to do what we would call an ingest transformation. So I want to add a new column. So when you ingest this row, say, hey, here's all the metadata, here's the vector. I want to add a new column that says is anomalous, yes or no, for some parameterized some way. And so every time a new vector comes in, I look at it and I go, oh man, this is really far from everything else. So let's flag it. Yeah, this is anomalous. That's a very powerful little feature. But typically I think of this in terms of like the user's use case. Again, I will use fraud transactions. Like you're sending transactions to me. We build a vector embedding of them, and then I can flag anomalous ones based on some criteria or some metric. That's very interesting to me as a feature of these vector spaces, sort of materializing the notion of its distance at time of ingestion. I think is actually a very powerful potential feature, and something I do think will become relatively standard, these kinds of ingestion time sort of transformations. But yeah, in terms of quality, I don't know. That's a great one. I want to write that down because I want to actually go see if there's anything here that maybe we should be thinking about.
Yeah, and even just in terms of simple schema enforcement of all of these other vectors have this number of dimensions, this other vector has n dimensions plus 1 or n dimensions minus 1, so I'm actually not going to allow you to insert that because it will not, it's invalid for this context.
So this is the one thing we do. I mean, like this is it. Like, so Rockset has arrays as a type, and by definition, so by our definition, arrays can be arbitrary length. So in theory, an array is like a list, basically. So you could have an array of size 4, and then the next row could have an array of size 7, and so forth. You're allowed to model it that way. And then for us, a vector is a fixed size array for a column. So we say, okay, this column has got to be vector of length 256. So we will check that. But that's about the end of it. Because the problem is once you have at least that, everything is valid. Literally if it's 256 integers, any list of those is valid. So there isn't really sanitization you can do beyond that. Like, I don't think there's any reasonable sense in which you can say like, oh, well, dimension 16, should have the high order bits should be 0. I don't think any of that makes sense. Like in some sense, vectors embeddings are trying to maximize their use of that space. So in theory, everything should be valid within that space.
Are there any other aspects of vector search, the ways that you're applying it at Rockset, the challenges associated with building capabilities on top of that we didn't discuss yet that you would like to cover before we close out the show?
I guess I would just reiterate the point that I'm a huge believer in kind of both the incremental and real-time components of vector as well as the metadata components, and that we are a strong believer in this. This needs to all be built together and unified, meaning I don't want to build a vector search that has metadata filter bolted onto it weirdly. I want to have a system where you can write a query that involves like metadata filters and vector filters, and they all participate together in one giant query with different indexes. And I have an optimizer that knows how to choose between them. If the left-hand side is really selective, it should do that part first. If the right-hand side is really selective, it should do that first, whether the vector's on the right or the left. Like it should have this massive thing that's built, that it plans, and all of the indexes participate together. And I think that is the best path forward for this, is kind of unified systems where the distinction between vector search and metadata filtering they're synthetic, in the same way that like in a database, using different kinds of indexes within your conventional queries is an implementation detail. It's not a thing that users should be worrying about. So I'm a huge believer in that path forward. And then for us in particular, the real-time component is super important for us. I want to be able to ingest vectors and have them available quickly. I want the searches to be quick. I want the searches to be fast. I want any metadata changes to be updated quickly. I think these are the core components of like what we're building and like how we're thinking about the path forward here. So yeah, I'll just reiterate that. I think we have talked about that, but.
All right. Well, for anybody who wants to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as the final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
I think that real-time analytics is behind. Us are behind in a way that has caused enormous problems to people. And a huge number of systems are abused because we don't have good real-time systems that are allowed. This is the problem we were trying to solve. But like, again, I don't want to pick on it, but if you go to any team that owns a non-trivial Elasticsearch cluster, they can tell you 6 different ways their Elasticsearch cluster is being abused, often for like real-time analytics. So I think that particular piece of our industry is way behind, and we're trying to catch up here. We're trying to help catch up here. The other one I will give you in an ML context, I think we data people have deeply failed to build first-class citizens for ML concept. So yeah, like I can give you rows and tables and whatever, but like an ML person wants features. They want features that have a specific computation that generates them. They want to track them over time. They want them version controlled. They want to A/B test them. They want to time travel them. All of this stuff can be built with enough work on your existing data platforms, but it's like the gap is really wide and bad. It's very unusable. And so I think data people have really failed to build usable primitive for ML and AI stuff. I think we have a lot of work to do here. And again, like the vector lifecycle stuff we were talking about today is just another example where we have a lot of work to do on top of what we've already built to make good primitives in an ML and sort of AI landscape. So those are two big ones, one in general and one for AI MLs.
Absolutely. Well, thank you very much for taking the time today to join me and share your thoughts and expertise on this problem of vector search, how to think about it, how to apply it. It's definitely a very interesting and valuable problem area, so I appreciate all the time that you and your team are putting into making it a more tractable problem. So thank you again, and I hope you enjoy the rest of your day.
Thank you for having me, and I hope you enjoy the rest of your day as well.
Thank you for listening. Don't forget to check out our other shows, Podcast.init, which covers the Python language, its community, and the innovative ways it is being used, and the Machine Learning Podcast, which helps you go from idea to production with machine learning. Visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. And if you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on Apple Podcasts and tell your friends and coworkers.